Hello guys, so this is a third example on exact differential. Now we have seen, so this is our fourth method. So remember, this is our fourth method on how to solve differential equations, first order differential equations. Now we are looking on example 3. Now, because we are conversant with this, we'll just go straight. We say our m of x, y should equal y squared. Now, and again, we are saying n of x, y should equal 2xy plus cosine of y. Now, let's perform Alexis-Cloud's theorem of partial mixed fractions. We are saying partial mixed derivatives. Now we're saying delta m with respect to y should give me, so this with respect to y alone, as you can see, it's just y to the third. Okay, so it's just so if I differentiate these, I should take 2 in front, y, then I should minus 1 to this power. So I should get this as my answer. Now, if I take delta n upon, with respect to x, I should get, now where there is a x, we should differentiate, and where there is a y, we treat that as a constant. Now we are getting 2y, okay? Treating this as a constant, treating this 2y as a constant, and then differentiating this x, I should get multiplied by 1. Then this is y, so because it's y and I'm respecting with x, so this is a constant, will go to a 0. Now, as we can see, we are getting 2y equal to y. So this differential equation is exact. So I'm saying the ordinary differential equation is exact. I'm going a bit faster. So for this case, we're saying once we have checked it's exact, we are saying delta m upon delta y is the same as delta n upon delta x. So do a small cross multiplication at this point. We are saying delta m dx, then we are saying do a separation there. We're saying delta n dy. Okay, now take the integral of both sides separately. So I'm saying the integral of delta m dx is the same as, now, so let's get back. So we're saying it's the integral of so what was our m? Our m was y squared. So our m is y squared, and we are taking the integral with respect to dx. So we have our x as a partial x at this point, so we're having an x to the 0 at this point. So we'll treat the y as a constant, then we are saying it's y squared multiplied by x. Okay, now, so we should add a constant of integration at this point, but it's not necessary as much. Now we're saying the integral of delta n with respect to x, to y now. Okay, so we should respect this to y instead of x. So we should respect this to y. We should get the integral of what was our n. Our n is 2xy plus cosine of y. So it's 2xy plus cosine of y with respect to dy. Okay, now we are saying, let's perform this integral. We are saying if we integrate this part, we are saying treating 2x as our constant, so it's 2x. Okay, then we should get multiply that by y to the second divided by second, add that to, if we integrate cosine, we should get sine. Okay, we should get sine of y. Now, once you have already gotten that, we are saying let's clean up this a bit. We are saying this is just x y squared plus sine of y. Now, having all these integrals from these both, so we are having x y squared plus sine of y, and again we are having from the top integral, we are saying we had y squared x. So for us to get our potential function, so I'll write, for us to get our potential function, which is our original function that had been differentiated using implicit differentiation to get our derivative that we are performing at this point. So we are saying f of x, so this is our potential function, should equal constant. Now we are saying f of x y is just similar as me writing all the terms only appearing as only appearing once. Okay, so I'm saying I'll write x y squared plus sine of y. As you can see at this point, y to the x as y squared x has repeated itself, so I'll equate this to a constant. Okay, so this is our general solution. So this is our general solution where if we are given an initial condition, we'll get the exact equation that had been differentiated using implicit differentiation to get this form. Okay, so please like, share and subscribe to my channel. Have a lovely day.